Hello, my name is Irina Kosteleva. I'm an Unconventional Resources Analysis Product Champion with KAPPA Engineering. Today we're going to be looking at the Permian Delaware example well in a RTA package Topaze. We're going to be analyzing data in various ways. We're using different concepts and then running forecast and sensitivity on the completion parameters. So here I have data already preloaded in the file. So you can see we have oil, gas, and water rates already loaded. The history of the well is about 1 year of production. Also, the pressure here is a composite signal. So if I go back to Edit QAQC, I can show that first 4 or 5 months of the well production, the well was produced by a casing. And then at some point, tubing was installed and the permanent downhole gauge was installed at the bottom of the tubing. So we have casing measurement for some time and then the sand face pressure measurement later on. So what I did, I converted the casing measurements to downhole and merged it with the sand face pressure channel. And then cleaned up the outliers. So we're going to be looking at this data here. So if I go back to analysis, this is the cleaned up, converted downhole pressure channel. Also, let's have a look at the PVT. The PVT is defined as a multi-phase oil, so it's a light black oil model with so it's saturated oil with water because the water saturation in the reservoir is about 50%, and it has a relatively high GOR, which is taken from a nearby well. So it's about 1200 SCF per barrel. So all of this is already predefined in the file. So we have already data loaded. So let's proceed with the extraction. And first, we're going to be looking only at the oil rate because that's our primary phase. And the first step of analysis is a single phase analysis. So we use the oil rate and the bottom hole pressure. So when we do extraction, we have a couple of plots generated by default. So the main analysis and diagnostic tool for us is the log-log plot. So I'm going to maximize it and zoom out. Because under tools, we already set up the horizontal multiply fractured well. That defines the straight lines that I have on the log-log plot. So you see I have parallel lines with the half slope indicating linear flow, then the unit slope line for the interference between the fracture, the SRV beep flow, and then the stabilization is showing the radial flow into the well from the outer formation, but it's way beyond the data from the well because permeability is very low, so we're not going to see it, but yet it's part of the analysis. If you're used to doing the square root of time superposition plot as a linear flow analysis, I have to warn you that it's important to look at the log-log plot first, because you can place a straight line through any part of data there, but you don't know where exactly the linear flow part is. Whilst in the log-log, it's exactly defined by the two parallel straight lines with a defined slope. So where exactly you put the slope tells you the parameters. And if you'd like to, you can double check this part. So you can create the linear flow plot. And if I do time interval selection and highlight this part, it shows the part where you have to draw the line to get your a square root of k. But without this log-log diagnostic, it's difficult to get that line precise because angle can be picked anywhere. So then these tools, you see they're interactive, I can drag them around, and they're associated with parameters. So if I go to Show Tool Parameters, I can see parameters, and if I move these lines around, the parameters are going to change. Same as if I move the stabilization, it affects my permeabilities, and other parameters recalculate from it, because this kind of holistic log-log plot approach ensures that you get a sensible interpretation of all the parameters compiled together. And of course, you need to input as much known information as you have. So for example, here we know that the well length is 9545 feet, and we can untick it to keep this parameter fixed, at least as the first iteration. So you see the position of the lines changed. Then we know that this well was completed with plug and perf completion technique. It had 42 stages with 15 fractures each, so that it will give us about 330 fractures in total with probably a short fracture half length. And to begin with, we will start with the 50% fracture efficiency completion estimate. So I will input 315 fractures as the first pass here. Again, the parameters change. And now when we drag the diagnostic lines around, we are limited by the parameters we have, and it's the other pair of parameters that is changing. So also as an input, we can get a general idea of permeability here. So I get in the range of 175 nanodarcy. Let's say it's 200, which is a reasonable estimate for Wolfcam. And then when we fix 3 parameters, it's only one that is left to change. It's the XF, and we can move it around to get a reasonable match. I can move more closer here. So we see that the transition happens a bit early in this case. So probably it's late, or probably some effects are happening in the reservoir. But we can see, at least with these estimates, what is our match going to be like. So we're going to match the first part of data and then see deviation in later part. So let me minimize the log and go to analytical model. Ideally, we do reset from diagnostic, but because we're doing it the first time, all the parameters are taken automatically. And then we click on generate. So the model, that's an analytical model. We have all the parameters defined. We have well length, permeability, number of fracs, half length. And we run, we recalculate rates from pressures. So we get a reasonable match at the early time, and we are underproducing at the late time. So we can run improve on XF or K, or both, but we're probably not going to run, not going to get a very good match for the entire history, because we know that also the pressure is dropping below the bubble point at some point, so we have multi-phase effects. So let's go into create a new analysis and call it numerical. But this is still a useful analysis because we estimated XF and K that can be used as an input into numerical models. So we're not starting from arbitrary values. We get something that reasonably describes our data. So I want to go to numerical. And here we have a button that says reset from analytical. So everything gets transferred into a numerical model automatically. So you see if I click that, you get multi-frag with 315 fractures. We get XF that we got from a previous step. Well length, and so on. So that will build a full numerical model. And as a matching and iterative process, we can start with using a simple trilinear model. So the geometry is simpler so that it allows us to model just a segment of the whole well instead of the entire well. And it's much faster for improve and iteration. But before doing that, it's important to go to PVT, numerical model, and tick use real PVT. So if you don't use that, the numerical model will be equivalent to an analytical in terms of PVT. So, and ticking this, we ensure that PVT parameters are recalculated in every cell of the model with corresponding PVT, corresponding pressure. So by doing this, we ensure that in every cell of the numerical model, when we know pressure exactly, we get the corresponding change in PVT value. So I click OK. Now go to numerical model, again reset from analytical, and I want to use trilinear model. So get the same number of fractures, half length, well length. I'm going to use 300 feet for the outer radius, because that's based on the completion, on the well spacing for this patch. Also, we need to define the initial state for this numerical part. So instead of bubble point, I want to use composition, and I can define the GOR that we know here and the water saturation, which is 50%. Also, I would want to generate pressure from rate and not rate from pressure. You can do both, but sometimes it's better to use one or another depending on the quality of the data. So then I click generate. And our control is set by rate. So you see we get the rate matching at early time and not the pressure and not other phases yet, but we'll get there step by step with the, that's our history matching part here. So the trouble here is that the permeability we used at the previous step was the effective permeability to oil. And here in the numerical model, the permeability is referring to the absolute permeability of the reservoir. So when we use multi-phase, of course, the effective permeability of each phase is reduced based on the rel-perm curves, which are defined in the PVT section. So as a step towards the match, I can try increase in permeability here. So I can keep the dialog open and go from 200 nanodarcy to 300 to generate. You see, I'm getting closer to my pressure match that I can go. This can be done manually step by step because you see the model runs in just seconds, or it can be done with a regression. But here, because I'm doing piece by piece match, okay, so we're getting somewhere close. And now we want to make sure, we'll get there in the consequent steps. I want to make sure that my phases are matching, but right now I don't see other phases on the plot, because remember the extraction was made on the oil rate only, and I want to add total rate to the extraction. So if I go to extract, you see here under production data we have oil rate, and using this button I can add additional phases. So I will take gas and water production to have them together. And my log is of course changed because now we add all the phases together using their PVT. We use them to an equivalent total rate, but we're not going to do analysis on this. We're only doing it so that our history plot displays all the individual phase rates. But I still want to do, it's a little trick, I still want to do the main extraction based on oil rate, because in that case when I use improve, I would be matching oil model rate to the oil rate in the history and not to the total rate. So I want to do extraction on oil rate as a reference phase and the total rate as a second phase. So click on OK. And my history plot is going to be updated, same as all the other plots. I want to new model generation, click OK. Okay, so we have these rates on the history plot now. I can actually close the linear flow plot. I don't need it here. So we can look at the rates. Again, the control is set by the oil rate. We can see that the gas rate is quite close. The oil rate is, the water rate is quite high, but that is explained by the fact that this is a injection water, so we can only match it in a full numerical model. And of course we have this breakout when we have the pressure going below the bubble point. So first of all, we can try to match the gas production a bit closer, because remember our GOR is taken from a nearby well. So I can go to numerical and change it a bit and keep the dialog open to see what's the result. So it's the same similar procedure to what we did with the permeability. So I get a bit closer, and then maybe 1400 will get me a bit high, and probably 1500 would be a good estimate for GOR. It's not too far from the initial part. Yeah, we get closer on the rates, because then I get good correspondence on the early part of the gas production is seen here, and then here I'll be dropping the pressure, so that part will be handled separately. And for the water and late time behavior of the model, we can use the relative permeability curves as the matching parameters as well. So of course they are highly uncertain in the unconventional reservoirs. So the change in the exponents, the parameters, the endpoints for the relative permeability curves becomes a matching parameter in this case. So here I can use some parameters that I've already gotten for this example. Just need to be careful. This one. So you see we get more streamlined flow, we lose less in the presence of the multi-phase. So I type some parameters, 0.25, and the power change to 1. So for oil and gas it's purely linear. And click OK. And once this is done, we can rerun the numerical model. And you see we get actually much better correspondence on each phase except to the early time water rate. And using the rel perms also help to match the pressure, so we get a decent match on all rates and the pressure as well. So we can use improve to refine a bit the pressure match on the K and XF. But it's not really needed in this case. So this model can be used to run a forecast now. So I create a forecast. So now that we have a decent history match, we want to run the model forward to get the recovery estimate. But before we do that, let's go to numerical and make sure we get rate from pressure as well, because our forecast is going to be constrained by pressure. So this model will also be rerun, and I want to make sure we include the constraints here. So you see we can have a model run both ways, rate from pressure and pressure from rate. So ideally, if you have a match, you get a match on both ways, but sometimes it's easier to do it on a cleaner or more reliable channel as opposed to the second one. And now I want to do the forecast on this model. It's going to be run for 30 years with a decline in pressure ramp. So it automatically picks the last pressure point and declines it to 500 psi. So the model is generated and we get our forecast. Now that we have a forecast, we're not really interested in rates, so I can maximize the log. Click on show and remove rates and display simulated cumulatives for oil and gas, and then I would reset the scale. So they come to the same point, but it doesn't mean it's the same value because we have two scales because it's gas and liquid totals on the separate scales. Also, you can do add the results in plot for the detailed. Then you can see the quantities in place because we used trilinear model with a limited extent boundary, and you have the forecast production. So after 30 years you have Q oil and Q gas, so you can divide it and get the recovery factors in place. So now this next step we're going to do is to run sensitivities. Sensitivity. So the next step is a sensitivity study on the completion parameters. So what we can do is to use the model that we found. So we can go to additional tools and numerical design. So that will, you see the dialog is already populated with everything that we had in our model. I want to generate pressure from rate this time. And if I go to history, I will only keep the oil rate. So that's my oil rate history. I'm taking the model with the matched parameters from our analysis, and I want to generate a new pressure. So I click on generate. So this is not an interpretation now that we generate clean pressure, and then use that as a control for a new rate forecast. So now it's running, and you see we have the oil rate, and the pressure is going to be updated in a moment. I only want to use the oil rate for this. Then I would regenerate the model with the forecast, only to then run sensitivity on the forecast and change the parameters individually. So that's what we had. And then I click on forecast and do exactly the same control as we had before, 30 years of ramp in pressure to 500. So far I'm just reproducing roughly the forecast we had before. Now that we have it, if I go to sensitivity, there are several options that you can run sensitivity on, and I want to run deterministic multivariate. It means that I would take a few parameters, in this case, a number of fractures and half length of fracture. I will vary each of them, and I will go through every possible combination of sampling for both of parameters. So if I say have 5 parameters for number of fracs and 5 parameters for half length, I'll get 25 combinations. So for the number of fractures, I will use 5 samples between 200 and 600 fractures. So here on the right, you'll see what are the values that are going to be used, so they're equally spaced. And for XF, I will untick log and take the XF between 30 and 70 feet. So my model value is currently 50. So I will do several combinations and click on generate. So I'll get 25 numerical models run. And because it's the trilinear simplified geometry model, it will run a bit faster. So once all of the models are done, we can see the forecast on the sensitivity plot. And of course, these are all the 25 models together. And if I maximize it under show, I can select some subsets of those to see what I would like to make decision on. So I would remove rates. And under cumulatives, for example, for the first view, let's select only cases with the XF equal to 40 feet. So we get different number of fractures, but the half length for each of them is the same. What you will see that after 200 feet, and I can add a legend here, that for 200 feet we get slightly lower EUR, but for other 4 cases we get very close result. And the difference is that we're optimizing the production, we are speeding up the reserve, so we're intensifying it, right? When we get the same XF with higher number of fractures, we don't really get a benefit in the total recovery. We just speeding up, we're moving that recovery earlier, so it can be completed by the economical analysis, and we can see whether this intensification of reserves makes sense. And I will create a copy of sensitivity to illustrate another idea. Sensitivity 2. And here I would like to compare cases when I have shorter fracs but higher number of them, or longer versus longer fractures but lower number. So roughly keeping the total half length the same, but seeing how that affects the results. So again, I would go to cumulatives and start with 600 fracs, 30 feet, then 540, 450, and so on. Okay, so in this case, you would see that you see the range of forecasts, but of course these completions would be very different in terms of the cost and the pump-in values. This analysis can be complemented by an economical estimate of the investment for into the well stimulation. So you can do different kind of sensitivities like that. And also, if we go back to the original numerical model, you can also start with the for example, create a copy of the analysis and change your permeability, saying what if it's another value. Then you can repeat the whole process, because remember, it's never a single deterministic answer that we're looking for. It's not possible to discern the effects of different parameters unless you clearly see all the transitions. It's more complex than the conceptual models that we use, but we give you a range of models, and you can find different matches with different permeabilities and estimate the uncertainty that you have on your parameters. Another topic, we can go back to an analytical case, and I would like to present the interpretation of the same data, but using a different concept, an anomalous diffusion, when we account analytically for heterogeneity in the reservoir. So, so far we used a horizontal multifrac well in a homogeneous reservoir, being an infinite or trilinear geometry, but still everything outside the well, we would assume to have the same properties everywhere. In fact, in most unconventional wells, we see the heterogeneous behavior. We see that there are many levels of heterogeneity, and the anomalous diffusion model allows to account for those complexities by homogenizing different levels, magnitudes of heterogeneity into 1 or 2 media. So you can homogenize everything in the reservoir, or use double porosity and say we have fissures and matrix. So let's proceed with doing an analysis with that model. So I would create an analysis copy of the first tab without keeping the model. And also I don't need a linear flow plot here. What I would like to add is a new plot that is called specialized line log-log. So it's exactly the same as our original log-log with a bit of extra functionality. First of all, let's add show group derivative. So that is a simple tool that's essentially pressure over 2 pressure prime that highlights any power law behavior. So whenever we have a straight line in our derivative, we'll get a stabilization in the show pressure group, and its value, the stabilization where we place this line, can tell us something about the flow regime we are in. So when this value of show pressure group is exactly 1, it corresponds to linear flow. And remember, initially we tried to match it with the 2 half-slope lines with the linear flow. It's close enough, but it's not exactly the value. And then we would try to see what the value here is. So I would do right-click and add lines, and then add a power law line. Click on create. So this adds 3 lines. The third one is added because I have show pressure group here. And they are interactive. You see I can move them around the plot. And the idea is to first place the show pressure group stabilization, because it gives you the value that you're going to use further. And then, as you see, as I move it, I change the slope of the other lines, because there's a one-to-one correspondence here. And when I'm happy with the parameter here, I would drag these 2 top lines, first matching the derivative, because that line is not affected by skin, and the top line can be above or below the second line. Once we place the lines, we can estimate the diffusion exponent from the slope, and in this case it's going to be about 0.76. So I would go to an analytical model, add the anomalous diffusion as a reservoir model, and I would also select it to be dual porosity as a slab. So we get these extra parameters that allow us to more handles to match the model. Because remember, when we use the standard model, we would not get exactly the trend in our data with an analytical model. So the diffusion exponent that we found from the show pressure group goes into secondary diffusion exponent, because we assume that what we see over longer time is the diffusion from the matrix into the fissures, natural fissures. And the diffusion in the fissures usually dies out rather quickly, so it's masked by other flow regimes, so we don't see it. But we would use it as a matching parameter. So I would adjust lambda as well to get a better initial estimate. And for anomalous diffusion with double porosity, we usually advise to use finite conductivity fractures with a lower conductivity, which is still very high compared to the matrix in this case. Okay, and I would do a generate. So you see, the only parameter we took from interpretation is the primary diffusion. So this model doesn't match because we only took the primary diffusion exponent. And now we need to bring our model closer to the data so we can drag the model on the log-log to be a bit closer. And we can also go to improve. And of course we get a lot of parameters now, but the improve is going to be smart step by step, starting from most uncertain, going to permeability and XF that you would only match in the late part, so you don't start by matching them. It's important to get a reasonable estimate from them. So we have omega and lambda alpha F that I mentioned that it's not seen in the data. And we can do a first improve on those parameters. So you see we get a bit closer just by changing those parameters. And the next improve step can be permeability. We can add permeability to the set of parameters that we change. But now we won't go too far from that permeability because we're close to the match already. So that's why we suggest to do improve in a few steps. So here's the match after improve. We're getting quite close, and it's useful to check the second model, the pressure from rate, because remember ideally we need to match both. So I can change it here, and we see that we need some more improve to match the pressure correctly. So I can go to improve, go back to those parameters that I already used, omega, lambda, alpha, f, k, and add xf. And because I'm running pressure from rate, my target is now going to be pressure. And I would like to exclude part of it, so it's more important to match on the later part in this case. So I would put a lower weight to the middle part that is still a converted data. And then run. And after the regression, we should get to a reasonable match. We see that the model is about to converge, and the advantage of using anomalous diffusion is that we don't homogenize everything that's happening in the reservoir into a single standard diffusion medium. We can split it into two, fissures and matrix, and the diffusion exponent for each media characterizes how heterogeneous each of them is. So you would account for many degrees of heterogeneity just by using a single parameter different from unity for conventional diffusion. We're getting there. And now the model is calculated. You see, we match the pressure history rather well compared to, if I go back to the first analytical model and rerun pressure from rate. Even if I run improve on this model, the general trend would be different, because remember the log-log plot showed us that we are not in a pure linear flow, so I can run and improve in this case on xf and k with the same target as pressure. And my general trend would be slightly off data, but anomalous diffusion with double porosity allows us to match higher productivity feeding from the fractures at the early time and going into lower productivity at late time, being fed primarily by matrix. So you see we get a decent match, and it's not as bad, but in certain cases you wouldn't be able to match the data with the homogeneous model, and it would be advisable to go into heterogeneous interpretation using anomalous diffusion. Thank you for watching this Delaware example video.